Very good evening, sir. Am I audible?
Yes, sir, Mr. Amit, you are audible, perfectly audible.
Thank you, sir. Thank you so much. Thank you so much. A warm welcome and very good evening to all dear participants. A resource person of today's session, Dr. Ashish Kumar Yadav, sir, and chairperson of today's session, Dr. Hitesh Khurana, sir. Now, we all know that Dr. Hitesh, sir, already chaired our few sessions. So, we all are aware about Dr. Hitesh Khurana, sir. Without taking too much time, now I would like to hand over the session to our respected chairperson, sir, to kindly lead today's session. Please, sir. Please, sir. Welcome, sir.
Thank you, Amit. Really grateful to you for not introducing me at length because
As,
I feel it's
as
really
per your request,
that's
sir.
uh, thank you very much. And indeed, now coming to the work. And it is really indeed a pleasure for me to introduce someone who is from a place which I call as my alma mater. And I think it would be a pleasure for all of you to know about Dr. Ashish Kumar Yadav. He is working as assistant professor in the Department of Medicine at Institute of Medical Sciences, BHU, Varanasi, as an expert in the statistics. And if you see his qualification, he is BSc in statistics, and thereafter he has done his MSc and PhD in health statistics. Besides that, he also holds a professional diploma in clinical research. And all these qualifications make him a perfect person to carry out the biostatistical research in any discipline of medical sciences. And if you see his further research professional interest, he is interested in multi-level modeling, a very advanced statistical technique, regression analysis, which is often used for the predictions and other kinds of making some estimates in multivariate statistics. Meta-analysis, the people are very fond of these nowadays. Bayesian statistics, a really very difficult field, but he is having a special interest in that. And besides that, he is also expert in the epidemiological study designs and the survival analysis. And with these kinds of interests and education, he has served at ESI Postgraduate Institute of Medical Sciences at Kolkata from 2014 to 2019. And he has also been assistant professor at Jhalwar Medical College at Jhalwar, Rajasthan. And he has also been working at National Institute of Medical Statistics, ICMR, which is a most prestigious body related with medical research in India. And he has also received various prestigious awards, which include the award for conducting high-end workshop under Abhyas scheme of Science and Engineering Research Board of Initiative Karyashala. And besides that, he has published about 35 papers, and he has taught in various institutes for more than 15 years. I welcome you, Dr. Ashish sir, and it would be indeed pleasure for all of us to get some insights about the statistics, about the special techniques on the about non-parametric statistics from you. Non-parametric statistics, of course, this is something which you really are afraid of, but I hope your words of wisdom will be wiser about that. Now I hand over to you, Dr. Ashish, sir.
Thank you, sir. And thank you, the committee, for considering me. And I'm really sorry to not, I am unable to open my video because it is saying to restart. So, and in a very short time, we will be starting the presentation. So I think sir has briefed me. Presently, I'm working as assistant professor in Center of Biostatistics, IMS BHU. Previously, I was associate professor at ESI Medical College. So I think, Amit, we can start the presentation.
Yes, sir. Yes, sir. Please, sir. Please, sir. Welcome, sir.
Okay, okay, thank you. So Give me a second, I'm just doing it. Okay, is the slide visible to everyone?
Yes, sir. Visible. Make it in a slideshow mode, so it
Yeah. Like that. Now it's okay.
perfect, sir. Perfect. Thank you so much, sir.
Okay, so once again, I welcome you all, and we'll start the presentation. And relationship or correlation studies or association studies in parametric and non-parametric frame, we will be talking about then. So basically, it's a very little broad topic, but I will try to make it as easy as possible. Okay, so relationship uh, has two special names with respect to parametric and non-parametric sense. Okay, now the very first question which should come to our mind is what is parametric and what is non-parametric. It's nothing but it's the nature of the data. Okay, when you are having some sufficient data and it is following a particular type of a parameter, uh, then we call it as a parametric distribution. Distribution theory is a little bit broad term, but in short, from a layman perspective, if we are talking about, so if we are having a good amount of data set and more or less your data is homogeneous, not a very heterogeneous population, then you can make some strong statements. Okay, but if your data set is a little bit small and is more or less heterogeneous, coming from a heterogeneous population, then it might be not following your parametric form. So in that case, it can be a non-parametric word. Okay, so to study the relationship, if the data set is following parametric distribution, then we call it as relationship as correlation. Whereas if the data set is non-normal, non-parametric, then we have the word association to study the relationship. Okay, so now coming on the things one by one. Now, the word correlation is used in day-to-day life to denote some form of association. Okay. In statistics, correlation analysis quantify the relationship between two numeric variables. So correlation is basically a study of two variables which is numeric and is generally quantitative in nature. When your variable is quantitative in nature, then we have the word ideal word of relationship as correlation. For example, we can have height, weight, we can have BMI and systolic or diastolic blood pressure, all these things. Okay, so now once we get that there is a relationship between the two variables. Okay, we know that if we come to know that the relationship is strong, then what we can do is that we can do some further mathematical treatment and we try to predict the variable on the basis of one variable. That means suppose we are studying the relationship between baby weight and age of gestation, and we know we somehow we got to know that the correlation is relationship is very strong. So what we can do at later part of the correlation is that we may predict that if age of gestation is increasing from this to this 37 to 34 to 35 week, so how much the baby weight will be increased. This type of prediction we can do. This is only possible when the correlation is very strong. Okay. Defining this mathematical relationship in the form of an equation uh, is a further step which we do after the correlation. Okay. But in this lecture, we will be focusing on the relationship only. Okay. Okay, now the very first thing, before jumping on the correlation or before jumping on really your broader big mathematical terms, what we should do is that we should have a graphical treatment of the problem. Okay, so by having the graphical treatment of the problem, if you want to study the relationship, basically you are studying at least two variables, then only the relationship can be studied. If you are having just one variable, then the variable we cannot study the correlation. We are generally that in that case we are having a univariate distribution. Okay, if you are having two variables at least, then we can have a bivariate distribution. More than two variables, then we can have multiple correlation and all that. So what we can do is that the first thing which we can before finding out the correlation, parametric or non-parametric or any regression thing, what we can do is that we can simply plot a scatter diagram. Okay, so scatter diagram, what it is nothing but it is the representation of two variables on a xy axis, where the y axis generally contains the outcome variable or the dependent variable, whereas on the x axis we have the independent variable or the predictor variable. So in the previous example, if I say age of gestation and baby weight, so basically baby weight is the outcome and age of gestation can be the independent variables, and we can have them on xy plot. And then we can plot the points. If age of gestation is this much week, what is the baby weight? If it has increased sometime, what is how much the baby weight in increase, and we can dot point the things. Okay, so by doing this type of plotting, we can have some idea about the relationship. So basically what type of relationship we can have is that we can get this type of scatter plot, where we would be having the response, and on the x-axis we can have the independent variables. So if you may get this type of pattern, increasing trend, a clear-cut indication that there is a positive correlation between the two variables. Here, here also a very strong correlation is there, but you can see that as the dose of the drug is increasing, your response is getting low. So at low dose, we are having a good response. Whereas when the dose is getting increasing, we are having a low response. That means a inverse relationship between the drug dose and the outcome. Whereas here we would be having the as the dose drug is increasing, we are the response is also increasing. So both the relationship is are very strong. One is having a positive correlation, whereas in the second one we are having a negative or inverse correlation coefficient correlation. Okay, now the correlation word is basically meant to study the linear relationship between two variables x and y. Here we are having a linear relationship. By linear we mean to say a line form. Here also we can see that a inclined line is there. Okay, but if you can have a correlation, or you can have rather the relationship between two variables, and the relationship might not be linear. Okay, here if you can see here in this third figure, here we are having the dose of drug, inverted parabola we are getting. Okay, so this is not the first order relationship. Linear line is not coming, we are getting a parabola. Okay, similarly we can have other forms. So this indication, parabola indication, is not a inference that the correlation is not there. Only it is saying that the correlation is there, but it is not linear in nature. Okay, it's of second order. Similarly, we can have more than second order also. As the order is getting increased, the inference will to make the direct inference become little bit complicated. Okay, so we would be focusing on the this linear relationship only. Now, coming on the types of relationship in the bivariate variables. Okay, the very first and the most popular one is the linear relationship given by Carl Pearson. Okay, so to quantify the strength of relationship between two variables shown to have a linear relationship on the scatter plot, we calculate the correlation coefficient. The coefficient takes the values between -1 and +1. For example, in this case, the correlation is perfect line. So it might be +1, and here we can have the negative -1. Okay. The plus and minus doesn't give any idea about the magnitude, but it is just giving you the idea about the direction. Okay. The number 1, 0.8, 0.7, 0.6, this all is giving you magnitude idea. Okay. So if both x and y, now coming on the condition when you can apply the Carr-Pearson correlation coefficient formula, if both variables x and y are normally distributed, we calculate Pearson product moment correlation coefficient R. Okay, so when the variables x and y, for example, if we are having height and weight, or we are having systolic blood pressure and BMI, okay, if both these variables, SBP and your systolic blood pressure and BMI, if both these variables you have the sample of say 30 patients, okay, and if SBP and your BMI both are following normal distribution, then only you can apply this correlation coefficient given by the Pearson, Carl Pearson. Okay. So, how to have the idea about correlation, normal distribution, I think this might have been covered in the past. Okay. So, a brief or say a layman idea one can have is that if the variable is continuous in nature, you can plot quantitative and continuous in nature, you can plot a histogram. Okay, and by joining the midpoints of the histogram, you can have a frequency polygon. Okay, so if it is following more or less a bell-shaped curve, and you are having the values of central tendencies close to each other, okay, then it might give you an idea about that the data set is following normal distribution. However, for a more scientific inference, we generally have some standard test. We have QQ plot, we have normal distribution test, Kolmogorov test is there. There are many tests which can test whether the data set is following normal distribution or not. Okay. If the data set is following normal distribution, then you can use the Carl Pearson formula to study the relationship between two quantitative variables. Okay, which are continuous in nature. So it is calculated as the covariance of two variables divided by product of their standard deviation, and the term product moment is the name derived from the mathematical nature of the relationship. So this basically we have this formula for Pearson correlation coefficient. We have xi, two variables are there, one is x and the second one is y. Okay, so what we can do is that we can calculate the mean. Suppose x is systolic blood pressure and y is BMI. So what we can calculate is that we can calculate the mean systolic blood pressure and mean BMI. And then this numerator term is basically called as your covariance term. Okay, the xi minus x bar, yi minus y bar. That means how much the values are deviating from its central value, the product of both the things. Okay, what's happening, divided by this formula. In the denominator, generally we try to standardize the covariance, so we are having this formula to make it unitless. So this is standard deviation, nothing else. Okay, xi minus x bar the whole square, yi minus y bar the whole square. So if x and y both are following normal distribution, then you can calculate the correlation using this Carl Pearson formula, and you would be getting the value of your correlation coefficient, which is denoted by R. I hope correlation coefficient is clear to everyone. Now, coming on the non-parametric part of the Pearson correlation coefficient. Okay, so this is the test also. This is also given by Carl Pearson only, and it has a special name. We call it as Spearman rank correlation coefficient. So when we are applying this, so if one or both the variables in the correlation analysis is not following normal distribution, that means either the previous example, if I take systolic blood pressure or BMI, both these variables are not following normal distribution, or any one, that means the SBP or BMI. If any one is also not following the normal distribution, then we can use a modified form of Pearson correlation coefficient that we are calling it as Spearman rank correlation coefficient. So as the name says, Spearman rank correlation coefficient. So how we can calculate it, this rank correlation coefficient is that instead of using the original values of the data set, say SBP, if it is not following normal distribution, what we are taking? We are taking their rank values. Okay. And then we are calculating the Pearson correlation coefficient between the two variables X and Y. So instead of using absolute values, we would be using the rank values for X and Y. If both X and Y's are not following normal distribution, we would be taking the rank of both X and Y. If X is not following, but Y is following the normal distribution, so we would be taking the rank of X and absolute values of Y. Okay. And then we can have the Spearman correlation coefficient. Okay. And it has a assumption that at least one of the variable is measured on an ordinal scale, and when the sample size is small, then generally we do not prefer Spearman correlation coefficient. In that case, we use another type of, and we have a lot of tied observations. In that case, we used another type of distribution which we are calling it as Kendall's tau correlation coefficient. So Spearman rank correlation, when we are using, if one of the variable out of the two is not following normal distribution, or both are not following normal distribution, and the data set is quite large and we have less tied observations, then we can have the Spearman rank correlation. The formula of Spearman rank correlation is same as that of your Pearson correlation coefficient. So instead of using absolute values, only what we will be doing is that we would be using their rank values. Kendall's tau correlation coefficient, as I have told, uh, Kendall's tau correlation coefficient is used when the data set is small and there are a lot of tied observations. You are allotting ranks. Okay, suppose systolic blood pressure is there, and suppose for a patient you have got SBP as 137. You might be having more than one patient whose SBP might be 137. Okay, now in that case, both the observations are having the same observation values, 137 and 137. In that case, what happens? A tied rank need to be allocated. So if you find in your data set there are many variables which are having the same values and a lot of tied ranks are coming, in that case a better measurement of correlation instead of Spearman is given by Kendall's tau correlation coefficient. Okay. This is the formula for calculating the Kendall's tau correlation coefficient. Number of concordance pairs minus number of discordant pairs divided by number under root of n1, where n1 is the number of data pairs not tied in the target features, whereas n2 is the number of data pairs not tied in another target features. Okay, now there are a few more correlation coefficients. I will be coming on that in them, but a general question which comes to our mind is that someone has written something. Give me a second. Okay. I'm audible to everyone, please.
Yes, sir.
Okay. I will address the individual queries. Okay. Okay. Now, give me a second. Now, correlation coefficient, uh, generally people used to ask you how much correlation coefficient value is a good measure of exact correlation. Okay, so basically, we do not have a very clear-cut answer for this thing. How much correlation is a very good correlation? It depends on your objective. Okay, for example, all of you must have studied the Ohm's law. Okay, so if there is a physical relationship between two variables, okay, in that case, the we should not get a single case which is not following that particular law. Okay, so in that case, 100% correlation is very good, whereas there are certain things where we have 80 to 90% correlation is considered to be a good one. Okay, so it depends on your objective. If your problem which you are dealing has a good amount of uncertainty, okay, that means you cannot make a guess about the outcome. Okay, it has a good amount of uncertainty. In that case, a broad classification of correlation is given as that if generally if you are getting a value of correlation R 70% or 0.7 or more than that, then it is an indication that there is a strong correlation. Whereas a value between 0.5 to 0.7 may be interpreted as a good correlation. A value between zero point 0.3 and zero point 0.5 may be treated as fair or moderate correlation, and any value which is less than zero point 0.3 would be a poor classification. Again, this last 0.3 or less would be a poor classification. It depends on your objective. Okay, what is your objective? In certain situation, 30% correlation is also considered as a good correlation. So how we can do is that what we can do is that we can perform a testing of hypothesis to test. Okay, so in the parameter you must have seen what we can do is that we can frame the null hypothesis and an alternative hypothesis. So null hypothesis would be whatever R you are getting is equal to no correlation, which is zero, and alternative that it is significantly different from zero. And you can have a test tool which is based on your T parameter in correlation coefficient. And if that test statistics suggests that the null is getting rejected, that means whatever the value you would be getting, it will be significant. So testing of hypothesis, a scientific approach might be used, can be used to check your correlation whether it is significant or not. From on a broad perspective, we can have these cutoff points. 0.7 or more is an indication of strong. 0.5 to 7 good correlation. Less than 0.3 might the correlation might be attributed because of the chance also. Okay, so this is the hypothesis testing, as I was saying, that you can perform the testing of hypothesis. Okay, so what you can do is that you can have a null hypothesis H naught R is equal to 0, HA alternative hypothesis that the correlation is not equal to 0, R is not equal to 0, and we can use the T statistics to check the relationship whether the null hypothesis would be rejected or not rejected. Okay. Now, once you get that you are getting good correlation, okay. So what you can do is that you can you want to have some better measurement or some more in detail, want to have a tool for that thing. So in that case, you can use coefficient of determination. Suppose you got a correlation of say 70 or 80%. Now you want to predict the one variable on the basis of the other one. So what you can do is you can have the you can go for a regression modeling or uh, type models. Okay, in that case, what we are using a tool which we are calling it as a coefficient of determination. Okay, so coefficient of determination is nothing but it's the uh, R square. That is, you simply multiply your correlation coefficient by itself. And if you are getting a correlation coefficient multiplying it, and if you are getting, suppose you have got the correlation as 70%. Okay, so 0.7 into 0.7, we would be getting 49%. That means 50% variation, whatever is happening in one variable, is caused by the other variable. Okay, so this is another type of inference which is more strong compared to your correlation. In correlation, what we are saying, strength of relationship is not shown. It is just saying as x is increasing, y is also increasing. Okay, and this relationship is this much, positive, negative, like that. But how much change in x is occurring because of y, this type of statement you can make when you are measuring coefficient of determination, which is nothing but which is a tool in which is used in your regression analysis. Okay, so always you find that coefficient of determination will be less compared to your correlation. So correlation very high is an indication that yes, you have got a good correlation. Now you can go for regression modeling. Now, as you can see that R square, we know that the correlation coefficient value lies between +1 and -1, and its coefficient of determination is generally the square of the term. So it is now never going to be in negative coefficient of determination. Always you will be having its value in the range of 0 to 1. Closer the value coming to 1 is giving you an indication that the relationship, strength of relationship between the two variables is very strong. So you can make a very good prediction. Given the value of 1, you can predict the value of other variable if R square value is coming close to 1. Now, coming on another type of your relationship, some more measures. Okay, so we have point biserial and biserial correlation coefficient. Okay, so point biserial correlation, point biserial correlation is a special case of product moment correlation, that is Pearson only, in which one variable is continuous and the other variable is binary. So when we are using point biserial correlation coefficient, when one variable is continuous, that means one variable can be SBP, DBP, BMI, and the other variable is binary. So binary means only two outcomes are there. So two outcome can be their gender, male or female, or diseased or non-diseased population, or smokers, non-smokers, alcoholic, non-alcoholic, like that type of things. Okay, so if you want to have the relationship between one continuous variable and one variable which is dichotomous in nature, in that case, a tool which we are using is the point biserial correlation coefficient. Okay, one of the assumption it holds is that it is assumed that for each value of x, the distribution of y is normal. For example, if x is your say cholesterol level, total cholesterol level, and y is your say binary variable, say smoker or non-smoker. So for smoker population, if y equal to say smoker, for smoker population, the values of your cholesterol should follow normal distribution, and for non-smokers also, this variable should follow normal distribution. Both the distributions can have different means but should have same variance. Okay, I hope the term means and variances are clear to everyone in the previous classes. Okay, so if they are having, this is basically called homogeneity, heteroscedasticity property. Okay, so both the variables are having same variances. In that case, we can calculate the correlation between the two variables. One is binary and the other one is continuous by point biserial correlation coefficient. Okay, RPV. Now, sometimes what happen, ki the variables, the dichotomous variables are not natural but is artificially dichotomized. Natural variables, for example, dichotomous can be gender, male and female. It's a natural variable. Both the variables are different. But you can categorize BMI, that if BMI is 25 or above, it is a case. So I am coding it as 1. If it is below 25, I am coding it as 0. So this type of uh, categorization into dichotomous variables is not natural, but you have categorized it yourself. In that case, we are using, instead of using point biserial correlation coefficient, we are using biserial correlation coefficient. Okay. Now, third one, phi coefficient. The phi coefficient is basically used, also denoted by your this R phi, is basically used when to study the relationship between two binary variables. Okay, disease present, absent, smoker, non-smoker, two types of variables, both are binary in nature. So in that case, if you want to have the relationship between two binary variables, uh, both are dichotomous in nature, in that case we can have the another measure of correlation, which we are calling it as a phi coefficient. It's basically having a non-parametric form. Okay, and in that case, if the distribution is equal, 50-50 split of are there of smokers, non-smokers, male and female, then the values of this phi generally will lie between -1 and +1. Partial correlation coefficient. Now partial correlation coefficient is basically, as the name says, we are having only a partial correlation between the two variables. Suppose, so in this type of variables, what we are doing is that we are trying to control the relationship between two variables. The third factor impact is getting controlled. So partial correlation is a measure of strength and direction of a linear relationship between two continuous variable while controlling for the effect of one or more than other continuous variables, also known as covariate. Okay, so let's look at one example directly to understand what we are talking about in this partial correlation. Okay, now we will not try to be more methodical. Now, look at this example. Studying the relationship between fertilizer and crop yield, keeping weather condition constant. So what we are doing is that we are studying the relationship between fertilizer and crop yield, and we are controlling the weather condition. Second example, studying the relationship between anxiety level and academic achievements while controlling for intelligence, IQ. Okay, so here we are just finding the Carl Pearson correlation coefficient only, but we are controlling for the third factor. Okay, that's why the name it is partial. So whatever the impact of the third factor would be there, we would be subtracting it from that formula. Okay, so there are certain assumptions for this to find out the partial correlation coefficient. Assumption 1, you have one dependent and one independent variable, and these both are measured on a continuous scale. You have one or more control variables, also known as covariates. They are should also be measured on a continuous scale. I hope continuous scale, you know what it is. Assumption third, there need to be a linear relationship between all the variables. That is, all possible pairs of variables must show a linear relationship. That means if you are plotting x and y, you must be getting a linear form, a line form pattern you must get. There should be no significant outliers. All variables should be approximately normally distributed. Okay. This is an example of both partial correlation coefficient, milk intake, body weight in kg, and age in years. So we just wanted age is an important factor which might influence this relationship. So what we can do is that we want to control for age, and we want to find out the partial correlation coefficient between milk intake and body weight gain. So we are applying the partial correlation formula, which is nothing but this formula we are using, x minus x bar, y minus y bar divided by, so we are finding out xy correlation, yz correlation, and zx correlation, like that. Okay, so partial correlation at the end, we are using this formula. So here you can see that we are finding the relationship between x and y, and we are controlling for the z, third factor. Okay, so we are subtracting the third factor. So correlation between x and y minus correlation between y and z. So whatever the impact of the z factor is there, we are subtracting it from the correlation of x and y. Okay, and accordingly we are subtracting it in the denominator also to find it, to form it in the standard format, and we are getting a value of 12% partial correlation. So the analysis revealed that there is moderately positive correlation between milk intake and body weight while controlling for the each factor. Multiple correlations deals with the situation in which correlation between 3 or more variables are required to be calculated. So then if you are studying more than 2 variables at a time, then you are dealing with multiple correlation coefficient. Okay, so suppose a farmer wants to find out the relationship between yield of wheat per acre, amount of rainfall, and average daily temperature. Then we can have 3 variables. We are studying 3 variables at a time. In the second example also, we have a military organization find out and the organization wants to find out the relationship between height, weight, and age. So in this case, we can have a multiple correlation. So multiple correlation to find out. Another example, you can see IQ, study hours, annual grade in percentage. So we can calculate it using partial correlation coefficient only. We can have multiple correlation also. So here, for example, in this case, if we want to calculate the multiple correlation coefficient, we can use this formula Rxy, Rx, Y, and Z, and we can find out the multiple correlation between the 3 variables x and y and z. So in this case, we are having a very good correlation coefficient between positive correlation coefficient among IQ and study hours with annual grade. Now, so whatever we have talked about basically when the variable is your continuous variable or quantitative data. Sometimes what happen, the data set is categorical in nature. Okay, and you have the groups as disease severity, say mild, moderate, severe. Okay, now you want to have, suppose there are two different physicians and they are categorizing the terms as individual as mild, moderate, severe. You want to find out the agreement between the two observer. In that case, we have a very good type of measure given by Cohen's Kappa in 1906. So what he has done is that he has chosen statistics to find out the correlation between the categorical variables. So in this case, suppose you have two readings. Reading number 1 by the first observer, he is classifying abnormal, suspect, doubtful, normal. Reading number 2 is also, second observer is also classifying the same group of individuals into 4 categories. Now this diagonal element, if you see, they are the element which are classified same by the both the observer. A proportion of individuals are there which are classified as abnormal by reader 1 as well as reader 2. F proportions are suspect by both the readers. K are doubtful by both the readers. So kappa statistics, if we want to have the agreement between the two things, what we do is that we have percentage agreement observed. How much the agreement is observed, that is the diagonal element, we need to plus it, minus percentage agreement expected by chance alone. So what is the chance agreement? We need to subtract that from the percentage agreement observed. Okay, and in the denominator also we have 100% minus percentage agreement expected by chance alone. So how to find out the first question which obvious comes to our mind is how to find out the this percentage agreement expected by chance alone. So how to find out the chance factor? So chance observation, if you want to find out, it's very simple to obtain, is that for this variable, if we, this cell, if we have to find out the chance cell value, So what we will do is that it is row total, whatever the total you are getting here, row total into column total divided by grand total. So you will be getting the expected value for this cell, this cell, this cell, and this cell. So if for A we have to find the row total, whatever the abnormals are there, that total plus column total A, E, I, and M total divided by grand total. That means all these cells totals. So like that we can find out the expected totals, and using this formula we can have the Cohen's kappa value. Cohen's kappa value, if we are getting 0.7, more than 0.7, indication correlation agreement between the variables. Any value if you are getting less than 0.5, then there would be a chance that it might be because of the chance factor. Okay, any value 0.5 or above is an indication that there is a good agreement between the observer. Okay, so let's look at a very small example. Here we have two pathologists A and B. Okay, and we need to find out the agreement between the two pathologists. They are grading it. Here we have pathologist 1 and here we have pathologist 2. So there is the diagonal element 41 is equally truly classified by both the pathologist as grade 2, whereas 27 are the slides which are classified as grade 3 by both the pathologists. So this is the this is the observed agreement. Okay, expected, we need to find out the expected to find out the expected, what we can do is that row total. So for this 41, row total is 44 and column total is 45. So 44 into 45 divided by grand total, that is 75. So 44 into 45 divided by 75 will be giving you the expected value for this cell frequency. Okay, so for the cell frequency, the expected value will be coming out to be 44 into 45 divided by 75. In this case, we are getting it as 26.4. Okay, so 41 is the observed value and expected values would be 26. So we could, for this diagonal element, we have to find out the observed values minus expected value, this formula. Percentage agreement observed minus percentage agreement expected by chance alone divided by 100% minus percentage agreement by chance alone. Okay, and then you can have the Cohen's kappa value. Okay, so we have studied the different type of relationship for parametric and non-parametric things, and then there are certain tests for the relatedness of the variables. So basically they are meant for your data set where we can have the association or correlation between the things. Okay, so basically we have four major tests based on relativeness. First one is your chi-square test. Then we have Fisher's test. Fisher's exact test is there. Then we have exact Yates correction, and the third one is basically the McNemar test. Okay, coming on the chi-square test. Basically the chi-square test, let's look at with the help of example. Okay, a sample of 600 people in a normal area had 28% slum area, 96% person had TB. Let the total population is 1000, and then we want to find out the relationship between the area and the tuberculosis. Okay, this is your data set. Okay, so we have the individuals with TB, without TB, and then we have the area where they are living. They are living in a normal area or they are living at the slum area. You know that in the past people used to say that tuberculosis is a disease which is occurring in a low socioeconomic strata. Okay, so we want to find out the association relationship whether TB is associated with the place of residence or not. So our null would be that there is no relationship of TB with the place of residence, and our HA would be alternative would be there is a relationship of TB with the area of residence, and we need to check it, test it. Okay, so we can test it using the chi-square test. So chi-square test, we would be using this formula: observed value minus expected value, the whole square divided by expected value. So if you can see that here, observed value is how much? 28. So for this, we need to find out the expected value. So expected values, as in Cohen's kappa we were finding, here also we can find in the same way. Row total, that is 600, into column total, that is 124, divided by grand total, that is 1000. Okay, so you can have that value 600 row total into column total 124 divided by grand total, that is 1000. So we are getting here 74.4. Okay, so this is the expected E1. Similarly, for this also we can find out the E2 cell frequency. So for each value, we would be finding out the observed value minus expected value, the whole square divided by expected value. So I is running from 1 to 4. 4 cells are there. 1, 2, 3, 4. These 4 cells. So for all these 4 cells, we need to calculate the expected values, and then we can test the hypothesis whether there is association between the two or not. Okay. Sometimes what happen is that the 2x2 table which we have made here, they are having very less number. Okay, so they are having very less number. In that case, what we is that generally the cell frequency is, if the cell frequency is typically less than 5, sometimes they say that it might be less than 10. Okay, so it's, if the cell frequency is less than 5, some authors says that if it is less than 10 generally, then we go for another form of test which is doing the same thing as the chi-square is doing, only is that it is taking care of the small sample size. Then we have Fisher's exact test. Fisher's exact test formula is this one: a plus b factorial c plus d, like that. I'm not going into the formula. Basically, I know that majority of you will not be using the manual calculation. We would be relying on the softwares, but we should know the theory behind the application, whatever we are doing. So if the cell frequency is less than 5 or 10, we go for Fisher's exact test. Okay, if the values are not less than 10, cell frequencies are not less than 10, and we are having two variables, categorical variables, where we are having count observations: diseased, non-diseased, smoker, non-smoker. If we have the count outcomes, in that case we would be using chi-square. Less than 10 frequency, we would be using Fisher's exact test formula. Okay, sometimes what happen is that we are having cell frequency less than 5, so a type of modification in the chi-square can be done. Okay, in that case, in the same chi-square formula only, we are generally subtracting 0.5, so it's a type of a correction factor in your chi-square test. Its correction is nothing but it's a correction in your chi-square testing. McNemar test is another form of a test. McNemar test is generally used in a case control study design. So I don't know whether the case control is being taught or not, but let me tell you that if you have matched pair for a case who is diabetic, you have taken another subject who is not diabetic but is matching with the case. So individual in the same house, you can take his brother as a control. Okay, given they are not very different in their age group. Okay, and that if you have such type of paired data or correlated data, where for each case you have a control, in that case, if we want to find out the relationship between the two variables, then we can do it using McNemar test. It depends, the test statistics which it is using is chi-square. Here we are considering the discordant pairs in our in the study design. So b minus c discordant pairs, the whole square, divided by b plus c. If n is greater than 30 and if n is less than 30, we generally use a correction factor minus 1, the whole square, and then we draw the conclusion for the McNemar test. So generally in a McNemar test, To find out the odds value, generally we used this test in a case control, matched case control study design. Otherwise, in cross sectional or your quad study design, we have the test based on your odds ratio, which we are finding out using the simple OR or RR values, okay, for stratified analysis, taking care of the your confounding and interaction and the things. So I hope I have done covered the topic. Okay. So thank you everyone, and now I would be trying to have the individual queries if anyone is having anything.
Thank you very much, sir, for very informative session. Now I request to all participants, if there is any query regarding today's session, then please write your query in the chat box. Either write in the chat box or simply raise your hand so I can send you the unmute request. We are waiting for your queries.
Okay.
All participants are free to write your query in the, either in the chat box or simply raise your hand so I can send you the unmute request and you directly ask with our respected speaker of the session.
There are a lot of applause for the speaker. I am seeing here in the chat box also, as well as the people are showing their reactions on the screen also. Thank you very much for that.
Yes, sir, definitely, sir.
Please put your questions also. So I think there are no questions for Dr. Ashish. Dr. Ashish has made his presentation very clear and very informative for the audience. And interesting thing is that he has covered from the basics and he has gone into details of the test also. And that too without any kind of calculations, which we are much worried about that. And especially his statement that okay, these are to be done with the help of softwares. That is really very useful because nowadays everybody is there for the saving his or her time and softwares are of great value.
Yes, sir. Yes, sir.
Definitely, sir, definitely. Thank you, Dr. Hitesh, sir, for sharing your views regarding today's session. And definitely, we received lots of feedback on YouTube and other platforms. And if there is still remaining any query, then you can mail us. You have our mail ID, official mail ID. Uh, Please mail your query as and don't forget to mention the subject as the name of the either our respected guest speaker or the name of the lecture. So I can forward that query to the respected speaker of the session. Now, on the behalf of Institute of Applied Statics and National Institute of Ayurveda, we convey our sincere thanks to all the participants for their active participation and commitment for today's session. We heartily thanks the guest speaker of the session, Dr. Ashish Kumar Yadav sir, who kept participants engaged by the very informative session. We also thanks Dr. Hitesh Khurana sir for sharing today's session and sharing his experience and views about the session with the participants. Now, this is the end of today's session, and tomorrow we again met with our respected speaker. There is one more session delivered on the inferential static cell session 5, testing of difference non-parametric test. So join earlier to avoid any technical issues.